And so here we have an RLC circuit, and it's also in parallel. That's a few things you might want to know here. So we've got a switch in the beginning. Before time equals 0, the switch is connected on this side. And when time equals 0, the switch is going to go to the other side, okay? So right now we're charging up our capacitor. That's the beginning. So at the very beginning, we charged up our capacitor, and then at time equals 0, I'm going to hit my stopwatch, and I'm going to flip the switch to this side, okay? And the question is, what is the voltage that's going to go through the capacitor as a function of time? That is our question. So in order to solve this question, we're not going to re-derive everything. I gave you all the derivations yesterday. We're just going to use the formulas, okay? In order to solve this, we need to analyze all the things that are going on here. The first thing that I notice is that if the switch is on this side, only the capacitor is going to charge, and the voltage of the capacitor is going to be the voltage of the battery. All right? So what we want to do is establish our boundary conditions, or our initial conditions. So the first thing I want to know is, what is the voltage at time equals 0? So the first thing I want to know is, what is V at time equals 0? So when time equals 0, this switch is now over here. Okay? So when time equals 0, the switch is over there. And we want to know what the voltage in this is at time equals 0. And if you remember, this was just a LRC circuit. The voltage of the battery is going to equal the voltage of the capacitor in the beginning. So at time equals 0, the voltage here is just going to be the voltage of the capacitor. So voltage at time equals 0 is equal to 4 volts. Now, another boundary condition that we wanted to know from yesterday's lesson was not just the function at 0, but the derivative of the function at 0. So the other thing that we want to know is, what is V, or D, how do we write that? dV as a function of 0 over dt. So this is going to be our second boundary condition that we want to know. The first boundary was this, we got that. And then for the second part of our initial condition is going to be the derivative of our solution to the differential equation. Okay, so how do we do that? Well, I'm going to look at just this picture right here, okay? And in that picture, what I'm going to do is use Kirchhoff's current loop rule. Let's draw that over here for a second, and we'll come back to this. So what I see is this. We have our capacitor. We have our resistor. We have our inductor. And that's it. And from yesterday's lesson, we talked about what this would look like. We would use the current loop equation. So we would have current some going this way. That would be IC. This would go down like this, IR. And this one would go through this way as IL. And then if these are my three currents, they're going to, add up to 0. So how do I want to write this? We'll write as IL plus IC, or IR, doesn't matter, plus IC is equal to 0. Okay, that's our Kirchhoff loop equation. From here, let's talk about what the currents from each part's going to be. Okay, when you first flip the switch, the current has two choices. This is the current right here. Let's just say it's going this way and it's going this way. Well, I could either go through this part or this part right here, but this is an inductor. An inductor doesn't want to change the flux. It's going to do everything in its power to go in the opposite direction. So the total current that's going through the inductor in the very beginning is going to be 0. So for the inductor, we have 0 plus. Now the voltage to the resistor, well, we just use V equals IR. In this case, it's going to be all the voltage. So it'll be 4 volts divided by the resistance R. In this case, it's going to be R is 0.5 ohms. And we're going to add to that the voltage of the capacitor. Now, how do we write? Because I'm writing everything in terms of, what am I doing here? Oh, yeah. So I'm going to rewrite the current right here. So the current can be written as, instead of IC, we're going to write it as C dV over dt. Now, if you don't know where I got that from, this is from yesterday's lesson. I'll quickly just do it one more time so you remember. With capacitors, you have the equation Q equals C times delta V. If you divide both sides by delta T, that's delta T right there, then this term right here becomes I. Okay? So you have I equals C, and then this term right here is really just C dV over dt. And so I of the capacitor is equal to C dV over dt. That's what I'm writing there. And all of this entire equation is equal to 0. Now here's the thing. We know this is 0.5, so is that going to be 8? I think 8. Yeah. So over here, you get 8 plus C. C is equal to 1 farad times dV over dt equals 0. So you end up with dV over dt, and this is dV at 0. So evaluated at 0 is going to equal minus 8 volts per second. And that is our boundary condition. So the question was, what is dV dt? dV dt is equal to, or let's see, dV at 0 over dt is going to equal negative 8 volts per second. Hopefully I haven't confused you so far. We found the derivative of our solution and we found a boundary condition for our solution and the derivative of the solution's boundary condition. That was required yesterday, and we had talked about that. If you don't remember why, go back and watch the video and then come back to here. Okay, so we have those two terms. The other things that we need to know are going to be our natural frequency and our Neper frequency, or the damping factor. And so alpha, which is equal to your Neper frequency, alpha, which is equal to the Neper frequency, is given by 1 over 2 times RC. Okay? Because this is a parallel circuit, this is what we get for parallel circuits for alpha. So you plug in for R, you're going to plug in 0.5, and for C, you're going to plug in 1. And what you'll end up for alpha is equal to 1 radian per second. And then the other term was the natural frequency. And the natural frequency, it doesn't matter if it's parallel or series. The natural frequency is always given by 1 over the square root of L times C. Well, we know what L is. We know what C is. We can plug in for L here. We can plug in for C there. And then you square root it. And you'll end up with 2 rads per second. So if you know this and if you know that, take a second to figure out what you would do next. Once you know what alpha is and once you know what omega is. Take a second to do that. You have 3 choices. Okay. A couple of more seconds. I'll let you write it down. Once you know that this is 2 and this is 1, you can conclude. Yesterday I wrote it as squared, but you don't really have to write them as squared. You can leave them as whatever, but let's do it as squared anyways because I did it yesterday as squared terms. So in this situation, omega naught squared is going to be greater than alpha squared. And yes, if omega naught squared is greater than alpha squared from yesterday's lesson, we would say that the situation is an underdamped response. Now, because we have established that this is an underdamped response, there's a solution that goes with the underdamped response. Remember, there were 3 different solutions we could have gotten. One was A1, A2. The other one was B1, B2. And then this last one was D1, D2. For the underdamped response, our answers are going to be, well, what this is saying is when you take the square root of your characteristic equation, you're going to get imaginary numbers. So you'll get 2 numbers that are going to be distinct and imaginary, but who cares about that? Because we know it's underdamped, we can use an equation that goes with underdamped. And the equation that goes with underdamped responses is, where am I going to write this? All right. Ooh, I got all the space right here. So the solution to the underdamped response from yesterday was given by, I'm going to run out of space here. I'm going to need this whole thing. And, okay, whatever. If you recorded it, all these decisions that I have to make. So let's see, we have this, and I'm just going to write alpha and the other term over here as well. So alpha was equal to 1, and omega naught was equal to 2. So we have that. Now, over here, I'm going to do the work. So for the underdamped, the equation was V as a function of t is equal to B1 e to the power minus alpha t cosine times omega damped, so that was omega damped, times t plus b2 e to the power minus alpha t sine of omega damped times t. So before we continue on, we have to figure out what omega damped is, this term right here. What is omega damped? From yesterday's equation, we said that omega damped was equal to the square root of omega naught squared minus alpha squared. Okay? And so that's just going to be 4 minus 1 square rooted. So square root of 3 is roughly 1.7. And this is a frequency, so it's going to be radians per second. And I'll put that over here as well. So omega damped is going to equal 1.7. All right. Now we can finally put in our initial conditions. So one condition was that the voltage of the source at 0, was equal to 4 volts. So all of this is equal to 4 volts. And then over here, we're just going to substitute for time for 0. So we get B1 e to the power 0 cosine of 0 plus B2 e to the power 0 sine of 0. And so from here, sine of 0 is 0, so this whole term goes away. And over here, you get 4 equals B1. E to the power 0 is 1. Cosine of 0 is 1. So we've established that B1 is equal to 4. All right. And once again, I'll put that over here. So B1 equals 4. So the whole idea of today was just to make sure you get some practice doing this. Okay. Next. What we have to do now is take the derivative. We have to take the derivative of this as a function of time. So V derivative of t. So you would have to take the derivative of all of this and the derivative of all of this. Here it's going to be a product rule, right? Because it's going to be e as a function of t and cosine as a function of t. And then you're going to add to it another product rule. I didn't show you that yesterday. I just told you that if we do it at 0, if we do all of this and then plug in at 0, the solution at 0 will be given by negative alpha B1 plus, is it plus? Yeah. Omega damped times B2. That's what you get when you plug in 0 after you take the derivative there. You don't need to do all that. This is going to be an exercise of calculus, easy stuff. So we don't worry about that. This is what we're after at time equals 0. And all of this at time equals 0 is equal to negative 8. So the derivative at time equals 0 is negative 8. And we can say that that's equal to negative 8. Okay. And then from here, we can plug in some stuff. So we get negative alpha, which is 1. B1 was 4. Plus omega, which was 1.7 times B2. And all of that is equal to negative 8. And then from here, you can solve for B2. B2 is going to equal negative 2.31. And we'll put that over here. B2 is equal to negative 2.31. Okay? And now we're finished. All we got to do is plug in all of our variables back into our equation, and we have solved our differential equation with the values. So let's do that. So we're just going to substitute everything in and we're done. So V as a function of t is going to equal B1. B1 was 4. Alpha was equal to 1. So it's e to the power, I'll just write it out, parentheses 1 times t. Cosine of omega, which was 1.7 times t, plus B2, which is negative 2.31 times e to the power minus 1 times t sine of 1.7 t. And let's just make it a little bit nicer, just because I like to look at things a little bit nicer. It's more aesthetically appealing anyways. There's an e here, there's an e here, you can factor it out. So we get e to the power minus t, that gets factored out. And you're left with 4 cosine of 1.7 t plus, or minus now, plus minus 2.31 e. Well, we don't want that e. E is already factored out, so sine of 1.7 t. And there is v as a function of time. So this is now applying what we had talked about yesterday. This was for the parallel circuit. Okay, so go over that for just a second as I erase the board and make sure that you understood the steps that I did. Because for the next question, we're going to do something similar. All right? So for the next question, we have a battery source. We're going, and it's 9 volts. We're going to be given a resistor, and that's 80 ohms. And then we are going to split our circuit, and you're going to have a resistor here. And that resistor is going to be 40 ohms. And we're going to have another resistor going this way. And that resistor is going to be 20 ohms. And what else do we want? We want a capacitor, and an inductor and a capacitor. So we'll have an inductor here, and then a capacitor here. So this will be 3 Henry, and this will be 3 farads. And from here, we have a switch. Okay, so, and our switch is actually going to open at t equals 0. So go ahead, draw out this picture here. I think I've got everything there. You do that for a minute, and I'll erase the other board. Okay, so for this problem, I hope you're following along of what's happening here, okay? At the very, before time equals 0, this switch is closed. So where's my eraser? This was what was happening in the beginning. In the beginning, you had this. It was connected. And then you let charge go through here, 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 and it happened for a long period of time, okay? Try to understand, think about what's happening if this was what was going on in the beginning. So if this was on charge and this was on charge, or this didn't have any current going through here, in the beginning, what would happen is current would go through here, and then at this point right here, some of the current would go through here, some of the current would go through here. Oh, look, there's an inductor, so current doesn't want to go through there in the very beginning. But after a long period of time, current is slowly going to go through here, and this is going to behave like a wire. And in the beginning, this will behave like a wire, but eventually, once the current starts to flow through here and charges this capacitor, then current isn't going to flow through there anymore. So just remember, in the beginning, even after you close the switch, you open the switch here, current went through here. It was going through here, but eventually stopped when this thing became some voltage, okay? What I want to know for this question is, what is the voltage of the capacitor as a function of time? What I want to know is, what is the voltage of the capacitor as a function of time when I do this at t equals 0? So when I flip the switch open, that's when time starts. Now what's happening? Okay, so to do this question, we need to ask ourselves, what are the boundary conditions? My face isn't showing up. Hold on. Hey, Google, turn on the living room lights. Okay, that's better. I don't think if that's better, but okay. So we want to know what our initial conditions are. So what we want to know is, what is the voltage of the capacitor at time equals 0? And we want to know, what is the change in the voltage of capacitor as a function of time at 0, or the derivative of the voltage of the capacitor. I'll just write it down and shut up. So the voltage of the capacitor at time equals 0. That is a condition we want to know. And the other one is the derivative of the voltage of the capacitor at time equals 0 dt. That's something we want to know as well. Okay, so let's establish that. This is a little bit more involved than the last question, but hey, YOLO. What color should we use? Let's use brown. I haven't used brown in a while. So when the switch is closed, in the beginning, when the switch was closed, we're trying to solve for what is the voltage of the capacitor at time equals 0. So what we want to do is look at when the switch was initially closed. So to do that, we're going to have the battery, we have our resistor, we have our resistor going down this way, we have our other resistor. Now, when the switch was closed, all the current was allowed to go through the inductor after a long period of time, which means the inductor just behaves like a wire. That's how I'm establishing it. And then you have a capacitor here. Okay, so that's the diagram I'm looking at. And I want to know what is the voltage of the capacitor before time equals 0, like after a long period of time when this thing was closed. This is hard, or it shouldn't be that hard, but it is kind of challenging. This part of the wire and this part of the wire are in parallel, which means whatever the voltage here is has to be the voltage here. I hope you agree with that. And so what values are we going to get here? Where'd my marker go? What we're going to end up with is the voltage on this capacitor. Because of the inductor, the polarity here is going to change. And we could talk about that another time. But for now, we would say that this thing is going to be negative on this side, and this side of the capacitor is going to be positive. So you've got a negative and a positive here. Now, if you were to look from this side right here, right? If we were looking from this side right here, current's going to flow through here, but we said current is not going to flow through here because when this is fully charged, current can't flow through there. Really pay attention to what I'm saying here because this is where it gets confusing. So just focus your attention as much as you can on this. The current is going to go through here, but the current will not go through here because this is a charged capacitor. It behaves like an infinite resistor. So if the current is going through down here, after this point right here, the only place the current can go is in this direction right here. The only way the current's going to go is in this way. It can't go that way because there's no current moving. This thing is charged. So what that means is that the potential here and the potential here have to be the same. So the potential here, this positive, and it's going to be negative here, the potential difference here and the potential difference here are going to be exactly the same. That's the only way current, when current gets to this point right here, isn't going to flow that way because the height of the mountain here and the height of the mountain here are exactly the same. So it has to go the other way. And what that tells me is that the voltage of the capacitor here is also going to be the voltage of the capacitor through this resistor right there. Okay? So, what is the voltage through this part right here? Because if we know what the voltage here is, then we know the voltage there. Now, I'm looking at just this. This is the only direction the current is going, in this direction right here. So you can ignore all of this at this point right here. You can ignore this and this. All we're looking at is this circuit right here. And if I asked you to tell me what the voltage through that point is, you could do that pretty easily. I hope. We use Ohm's law or whatever. So the first thing we need to do is figure out what the equivalent resistance between these two is. This is an 80 ohm resistor, and this was a 40 ohm resistor. So the equivalent resistance is equal to 120 volts. And then we can figure out what the total current is. So the total current, I, is going to be equal to the voltage of the source, that's 9 volts, divided by the equivalent resistance, 120 volts, ohms. And that's going to equal 3/40. So that's the current. That's the current that's going through here and here. Now, if we want to know the voltage through this source right here, well, we just multiply the current by the resistance. So the voltage through the capacitor, because we're going to call it the voltage through capacitor, is going to be equal to I, which is 3 divided by 40, multiplied by R, which is 40. And so what we end up with, the voltage of the capacitor is going to equal 3 volts. Here's where you gotta be careful, and this is why I kind of emphasize the polarity here. This side is positive. This side is negative. So that means this 3 volts isn't 3 volts. It's actually negative 3 volts. So the polarity in this situation matters. So the voltage of the capacitor is going to equal negative 3 volts, or the voltage through this resistor is going to be negative 3 volts, and therefore it's going to be negative 3 volts there. Okay? And that's the voltage of the capacitor at time equals 0. I'm hoping you got that. That was a lot of little technicalities to do to get that boundary condition, but that's what it is. So just remember, you're going from the negative to the positive, which means the actual voltage drop is not positive, but a negative. Okay. Where am I going to put that, though? I'll put that over here under my boundary conditions. So the voltage of the capacitor at time equals 0 is negative 3 volts. Next, I'm going to erase this really quickly. We don't need that. I'm going to put the inductor back. Because the next thing I want to do is figure out this term. V dc at time equals 0 over dt. That's the next thing I want to figure out, okay? So what is the voltage of the capacitor, the derivative of the voltage of the capacitor at time equals 0? That's the next thing. How do we know which side is negative and which side is positive? So if you have an inductor here, it's going to change the polarity of your situation. So typically, what you would get if you didn't have the inductor is the positive of this plate would be the positive of this plate, because positives are accumulating on this side right here. But because we have an inductor in series with the capacitor, it'll change the polarity. So this will actually be negative than positive. So as a rule of thumb, just remember that if you have an inductor here in series with a capacitor, it'll flip the sign. If you didn't have this inductor at all, then this side would be positive and this side would be negative. But once we include that, it will change the polarity. Okay? That's the best answer I could give you for now. We could talk about it more later on. But that's kind of the rule of thumb. Are we good? Zoe? Okay, good. So let's talk about this now. Okay? Now, here's something that you want to make sure you understand. whatever the current through this inductor is, has to be the current through here, because this is in series. So when the current goes through here, it also has to go through there as well. So we can say that the current of the inductor, the current in the inductor at time equals 0 is going to equal the current through the capacitor at time equals 0. Okay? And the current at time equals 0, while this thing was fully charged, the current through the inductor or the capacitor was equal to 0. There was no current going through. Oh. When you open this switch, when you open, okay, good. When you open this switch, right, we said that this was behaving like a wire and there was no current going through here. Now, when I said close, when you open the switch, so when you open this switch finally, then you only have this part of your circuit because this thing is open. You don't care about this anymore. Once this switch is open, nothing's happening here. It's all what's going on here. At the very beginning, you have all this charge that's built up that wants to move. But induction, remember induction? It doesn't want to change the flux. So if this was 0 in the beginning, if there was no current going through here, at time equals 0, there's going to be no current going through the inductor, because if there was, then there would be a magnetic then you would be changing the magnetic field. So there's going to be a magnetic field here. And when you open this, the current is only going to flow through here, which would change the magnetic field. And it doesn't want to change the magnetic field. So the current's going to try to remain 0 here so that the magnetic field here doesn't change. Okay? So then the current through the inductor at time equals 0, because it doesn't want to change, has to equal 0. And because the current through the inductor is the same current that's going through the capacitor, we could say that the current at the inductor times 0 is going to equal the current through the capacitor at time equals 0. And they're both equal to 0. Now, why am I even mentioning that? Well, here's the thing. The current through a capacitor at time equals 0 is given by this equation here. C times dVc at time equals 0 over dt. I did that from the last question. The last question I said, this is how you can establish current. Current is equal to the capacitance times dV dCt. And look at that. This is what we're trying to solve for. Well, we know this term. We've established that this is equal to 0. Okay? And so if we divide everything by 0, so let's just put that there. This term is 0 is equal to C times D, voltage of the capacitor, 0 dt. The C goes away, and we establish that the voltage of the capacitor, the change in the voltage of the capacitor as a function of time at time equals 0 is going to be 0. Please, I beg of you, make sure you understood that. It took a lot of time for me to actually explain to you how I would say that out. So we write our equation here, and then we take what we just got from there, plug it into here, and then solve for dVc, this thing, and it's going to be 0. So that will be our second condition. It's going to be 0 here. Now, we don't need to do this. But let's just, I'm just going to ask you. When this switch is open, we don't care about this. This is what we have, okay? So if this is what we have, could you tell me what is the voltage of the capacitor after a long period of time? What do you think the voltage of the capacitor would be after a long period of time if this was my circuit only? So this was charged in the beginning, and then I let it run. After a long period of time, what is the voltage of the capacitor going to be? Anybody. It is going to be 0. This is a damped oscillator. You have this and this. That's right. These two would make it oscillate forever, the voltage, but you've got resistors here. And these resistors are going to make the electric field here and the magnetic field here, that energy, it's going to be transferred into heat, and it's going to disappear. So if we were to graph this, what we would see is something that looks like this. And it oscillates and it goes to 0. So this would be voltage as a function of time. So the voltage would oscillate and then decrease. Okay, and we would approach 0. Good. Okay. The next thing to do is figure out what our Neper frequency is and what our natural frequency is. And we can then figure out what kind of damping we have. Do we have overdamped, critical damp, or underdamped? So let's do that. The natural frequency is equal to 1 over the square root of LC. So here, L is equal to 3 henries and C is equal to 3 farads. So you get 1 over the square root of 3 times 3, and that's going to equal 1 over the square root of 3. Now, what about alpha? I'll be back a second. Try to figure out what alpha is. Okay, so for alpha, it's going to be R divided by 2L. This is a series. This is a series RLC circuit. So alpha is going to be different here. That was the one thing that we took away from yesterday. And so here, our resistance, well, let's see. Whoop. Our resistance is this resistor and this resistor. They're in series. So the total resistance in this loop is 60 ohms. So we get 60 ohms divided by 2 times L, which is 3. So 2 times 3. And that's going to equal 10. And this is radians per second. And this is radians per second. And from here, we established that alpha squared, or just alpha, I don't know why I keep writing squared, but whatever. Alpha squared is going to be bigger than the natural frequency squared. And if that's the case, we are dealing with an overdamped. In the last problem, we did underdamped. Now we're doing overdamped response. Okay, and I'm just going to put my terms over here just so I can bookkeep, as we say. So the natural frequency was 1/3, and the Neper frequency was 10. Okay. Now, the equation to this differential equation is going to be exactly the same as for voltage as it is for current. So the way we solved it yesterday was for current, but because current, it's in a series circuit, the voltage is going to be the same. It doesn't matter. So we can rewrite our solution. This is the overdamped. The overdamped solution is going to be given by voltage of the capacitor as a function of T is given by A1 e to the power S1t plus A2 e to the power S2t. Where we can do, in our problem, we wrote current as a function time, but we're using our boundary conditions for voltage. So we can do this exactly for voltage as well, okay? So here's our problem, and what do we have to do from here? Well, we don't know what S1 and S2 are. We have to solve for S1 and S2. S1 and S2, if you remember, were the characteristic equation, the solution to the characteristic equation. So if you forgot S1 and S2, let's write it down. S1 was equal to negative alpha plus the square root of alpha squared minus omega naught squared. And S2 is going to be the other solution to that. So we also call it the complex conjugate. So that'll be negative alpha, just like before, except instead of the plus sign, it's going to be a minus. Because if you remember, this is going to be some sort of imaginary thing going on here. Well, no, it's not imaginary. Never mind. Ignore what I said about imaginary. This is an actual number. This will be a squared minus omega naught squared. Okay, so in the last question is what I was trying to say. In the last question, we didn't have to do this because in the last question, it was omega was bigger than alpha. So if I plugged in there, I'll get imaginary numbers. And so we can't use S1, S2 to solve when we're talking about imaginary numbers. In this case, alpha is bigger than omega, so that's why we use this solution right here, okay? So you can plug in those numbers. You can plug in for alpha is going to be 10, so negative 10 plus 100 minus 1/9 squared square rooted, and you do the same thing for this term right here. Should I just give it to you, or should I let you do it on the calculator and wait? Akene, what do you think? Would you like the answers to this? Let's give you the solution. So for S1, I'll write it over here. For S1, we will get 0. Is it negative? Yes, negative. Oops. So we'll get negative 0.006. That'll be for S1. So negative 0.006. And for S2, you will get negative 19.99. Negative 19.99. Okay. All right, let's keep going. Let's keep going. We're on good terms right here. Now let's put in our boundary conditions, everything we know except for A1 and A2. So for our first boundary condition, it's the function at time equals 0. That was our initial boundary. And we said that at time equals 0, it's equal to negative 3 volts. So this is going to equal negative 3 volts. And that's going to be given by, now over here, we get A1 e to the power S1 times 0, it's 0. You might be saying, well, what was the point of doing S1 and S2 if I'm just going to plug in 0 here? I have to take the derivative of this as well. So hold on there. Plus A2 e to the power 0. And so we end up with negative 3 volts is equal to A1 plus A2. This is our first equation. We have 2 unknowns and only 1 equation. That's a no bueno. You don't want 2 unknowns with 1 equation. This is why we need the derivative. So the voltage, the derivative of the voltage of the capacitor at time equals 0, dt, well, that was equal to 0. So we say that's equal to 0. And now we're going to take the derivative of this. So when we take the derivative of that, we get is equal to A1 S1 e to the power 0 plus A2 S2 e to the power 0. And so we end up with our second equation. My second equation is going to be 0 is equal to A1 S1. Well, what's S1? S1 is equal to negative 0.006 minus A2. And I'm putting the minus sign here because S2 is a negative value. So A2, 19.99. Okay. And there is our second equation. We've got equation 1 that only has A1 and A2. And we've got equation 2 here that has A1 and A2. You have a system of equations. You got to love linear algebra. You got a system of equations, and you can solve for A1 and A2. I'm going to erase this. You don't mind? You don't mind? You don't mind? Thanks. So working that out, if you solve for it, here's what you're going to end up with A1 and A2 if you actually work out the two terms. You'll get A1 is going to equal negative 3. Whoa, it's already 1250. Wow. Negative 3.0008. And what are the units going to be? Well, this is unitless, so if this is in volts, this has to be volts. And A2 is going to equal 0.0008 volts. And finally, we've got everything. We've got everything we need to plug back into here and write down our differential equation, the solution to our second order differential equation. So the voltage of the capacitor at any time t, when t is greater than 0, greater than or equal to 0, is going to equal A1. So that's negative 3.0008 e to the power S1. Now S1 was negative 0.006 multiplied by t plus A2, which is 0.008. That's kind of hard to do from over here. I'm kind of impressed with myself. E, that's a terrible E. I am not impressed with myself. E to the power, now S2 was equal to negative 19.99. So it would be negative 19.99 and then t. And there we have it. Okay. So those are examples of how you would utilize. I didn't want to just give you the theory. I thought it might be more practical to actually, once you have all the stuff that you need, now you can actually apply it to get some values. So this is how capacitance would change as a function of time. And let's just see if that actually holds true. If you said the voltage at time equals 0, right? At 0, this term would go to 0, this term would go to 0, and you would end up with roughly negative 3, right? It would, well, no. You would end up with negative 3, perfect, because it would be 3.008, negative 3.008 plus 0.008, and you end up with minus 3 volts. Bam, 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 bam. And then the other thing is that time equals infinity. If you plug infinity into here, you get e to the power negative infinity, that's 0. So you get 0 times this, gone. And then over here, you also get 0. So this term is gone. So at time equals infinity, you get 0 capacitance. We are good.